Alrighty, hello. So I am Christian, the current president for STARR, and I am going to be showing you guys a little bit on how to design an L1 level rocket. So this is a rocket for car that is L1, so that means it will be flying an H motor. We'll be kind of going over every part of the rocket design, a little bit of the manufacturing as well. But there will be timestamps throughout the whole video on certain sections that are important. So if you need to, skip ahead, but I would highly recommend watching the video in a whole. And then to start off with Openrocket. So Openrocket is a software that we use and most people use for designing rockets at this scale. So it's very important that if you don't have Openrocket, go ahead and install it. There will be a link in the description. But the way that Openrocket kind of works is we work top down. So when I say top, that's around about our nose cone area. So let's start at our nose cone. So we can just click on sustainer, our only option here, kind of the overarching term for our rocket, and we can click nose cone. So now there's a lot of things to start off here that are pretty important. So nose cone shape. There is a whole bunch of different shapes that you guys are free to play around with. For some kind of knowledge, we normally use OGIV or hack series, and if this shape parameter here is 0 in hack series, it makes a von Karman, and that's the one that we fly most often. But I like OGIV, so I'm going to go OGIV, but feel free to play around with this. And then important thing is the material. So almost all nose cones that you guys will be making for L1 level will be 3D printed with either PLA or PETG. Now they have very similar densities, so if I go over to PLA and PETG, you can see they have the same density. The only difference is PETG melts at higher temperatures. So if you're planning on going faster, PETG is a good option, but honestly PLA works fine. So we're going to click PLA. Choose our material, and then now the diameter. Let's talk about size here. So for STARR's L1, we're most likely going to be aiming for you guys to use a 29 millimeter motor, which we'll get into a bit later. And basically, as long as your rocket is as big as that or bigger, you're good. But it's very difficult to make skinny rockets. So my recommendation would be, at least at this scale, since you're flying a 29 millimeter rocket, maybe something like double, around about 60 millimeters is fine. You can make that smaller and you can definitely make that bigger. This is kind of just an engineering decision and seeing what works best. And then our length. So normally it's either a 3-to-1 or a 4-to-1 ratio, most commonly a 4-to-1. So we've flown 3-to-1 a lot, but I'm just going to choose a 4-to-1 ratio here. And what that means is our diameter times 4 is what we want the length to be. So that is just 240 millimeters. And that gives us kind of a relative shape. Now, it doesn't have to be these exact ratios. Those are kind of just recommendations that work best aerodynamically. But yeah, that's kind of a start there. And then wall thickness of 2 millimeters with PLA, I'm just going to keep it at that. We can go back and change that if we need. But that's basically our nose cone. So you can go around here, you can try out different shapes, but I'm going to click on OGIV. Now, there's that. So now we can move down a little bit and our body tube. So our body tube is automatically going to be the same ID and OD as our nose cone. It's nice like that. So the only things that we really have to fill in is our material and our length. So let's start with our material. So most likely for your L1s, you guys will be using the fiberglass that we have. So again, you're free to make this out of any material. You can get a thicker cardboard that you can buy online. You can do what some people have done before, lay up some funny kind of material. Jeans have been done before. So yeah, the sky's the limit here, but fiberglass is for sure the most common. And then moving on, let's say we've decided to go with fiberglass. It's around about 0.5 millimeters per layer of fiberglass. It's a very rough estimate, but it's not a bad place to start. And for L1 levels, you guys don't really need more than 4 layers. So I'm going to stick with 4 layers. 4 layers nicely works out to be 2 millimeters. So perfect. We don't even have to change our wall thickness. So everything here except our length is pretty good. So for length, honestly, I don't fully know how long I want it yet. This looks a bit short, so I'll make it a bit longer. You know what? Let's go ahead and make it even longer. Sure. This is completely subject to change. Let's just start here. All right. So before we keep heading more down, let's talk about our nose cone and how it's attached. So if we click on our nose cone and we go over here to our shoulder, the shoulder, basically, you can think of it as the coupler for our nose cone. So the coupler, if I go ahead and make coupler, and the general rule for couplers is you want it to be at least one caliper length. So caliper is just the diameter of your rocket. This rocket's diameter is 60 millimeters, so the length is also going to be 60 millimeters. Diameter, I think, would be 58 because of our thickness. And then a thickness of around about 2 millimeters, because this is also going to be made out of the PLA. It's going to be printed all as one with the nose cone. So you can see on the inside here, it's kind of sitting all nice and snug inside of the airframe. So what this will do is actually allow us to attach the nose cone, and the nose cone can still slip off in later times when we want to do recovery. But super simple here, nothing crazy, just making sure your diameter and length and thickness is all good. And yeah, so there is our nose cone a little bit more finished. Now let's keep on heading down. So the motors that we're going to be using are Pro 29s from Cicerone, so that means that they have an OD of 29. So to do that, since our motor definitely won't fit inside of this airframe right now because this airframe is way too big for it. So what we want to do is add an inner tube. This is also what we normally call a motor mount tube. So I'm going to go ahead right away and rename this to a motor mount tube. And this is most commonly made out of cardboard because it doesn't normally have to take a lot of force depending on how you set up your thrust structure. And its real purpose is just to hold the motor nice in the middle of your airframe. So all of these things here, I'm just going to keep as default. Most likely you'll find from the parts library, if I just whip this over here, you'll find what you're looking for because we might send you guys different kinds of motor mount tube pre-made. Something like these SDs BT, I think it would be 60. But yes, you can also choose from here. But just match the specs that you can find online, which we'll go over in a sec. So I'm just going to keep it as simple like this. This is going to have to change, but let's now say that this inner tube, which I'm calling the MMT or motor mount tube, is a motor mount. So this tells Openrocket where to actually put the motor. Okay, so now comes the important decision of what kind of motor do we want to fly? So if we search up pro38.com, head over to products, head over to Pro 29 reloadable rocket motors. Here is all of our choices. So pay attention to this underlined numbers here. This is kind of what you're going to be looking for. So since this is an L1 level rocket, you guys have to choose an H motor. You cannot fly this I motor, and these F and G motors, those are too little, so you have to fly an H motor. So kind of the rule of thumb from 4 grain to anything from 4 grain up works pretty well. So if you're curious, here are all the different kinds of propellants. A lot of them have videos, so you can go ahead and watch them and choose what looks the coolest to you. But I know that I want to fly. Let's see. Let's fly this blue streak. Why not? Yeah, sure. This guy right here. So again, you're going to have to kind of go through here and choose because it's important that it's an H as well as this number following the H is the average thrust. So it's also, well, it's listed right there. So the one I chose, this blue streak, has 200 newtons of average thrust. Slightly on the higher end, but nothing crazy. A good thing to kind of fiddle with is if your stability is too low, sometimes going for a motor that burns a lot faster is better, but we'll get into that in a little bit. Here's our total impulse. Here is the burn time, and then this is peak thrust in pounds. And then these are the delay charges, which we'll go over when we go over recovery. So this is the guy I want. Now we can go over to our motors and configuration, and we can go new configuration. Gonna move this guy over. So I can just search for that motor. Shows up right here. I am going to choose that. And now we can see that obviously we need to go ahead and fix our motor mount tube because it does not fit. So inner diameter 29 millimeters. There we go. That looks a lot better. And then now for length. So you can see it's red tube down here, right? So if I keep increasing this, the general rule of thumb is it needs to be kind of at least half of your motor. But to be completely honest, normally I go all the way up until basically right by the end. So I'm going to go to like, I'll say like 250. Oh, not 150, 250. Yeah, that's pretty close to the end. I think I'm pretty happy with that. So I'm going to keep it at that. Wall thickness of 1. There we go. Okay. So there is our motor mount tube made out of cardboard. So now this tube is just kind of floating there, right? So we need to have something holding or centering this motor mount tube within the airframe. So kind of alluded to what we need, but we need centering rings. So I'm going to click on centering rings. And then now you'll see it starts all the way down here at the bottom. Where you place the bottom centering ring and the upper centering ring, we will get to when we talk about rail buttons. But for now, I am just going to move this up a little bit. And centering rings are almost always made out of plywood. And then for our thickness, most common is around about quarter inch. So we'll go 0.25 inches. Automatically does our outer and inner diameter, fits up real nice there. Okay, so that's nice for the bottom, and then now we need one more at the top. So I'm going to click on body tube to make it a subclass of body tube. Another centering ring, and then now this guy I'm going to put higher up to the top. There's perfectly fine. Inches 0.25. Alrighty, and it's going to be made out of plywood. Perfect. Okay, so you can see I just kind of really quickly put one close to the bottom and one close to the top, because the whole purpose of this is to keep the motor mount tube aligned, which then keeps the motor aligned. So to keep it nice and aligned, it's easier if you have them furthest away from each other like that. But we'll get into, when we talk about rail buttons, a little bit more specific on how to place those. All right, so let's keep working down, and now we can head all the way to the bottom. The favorite part of building rockets, honestly, is our fins. So we can click on body tube because they're going to be attached to our body tube, and right up here we have 3 real options for fins, ignoring tube fins. If you ever want, you could search up tube fins, but they're you guys won't be flying them for L1s. So trapezoidal, elliptical, freeform. To be honest, it's normally only trapezoidal or freeform that you will use. Trapezoidal is really easy, so I'm just going to go ahead and choose trapezoidal. Okay, so now we have lots of options here. Let's start over with material first. So these will also normally be made out of plywood. So I'll go like that. And then for thickness, these will also be normally, they could be a quarter inch. I'm going to go over to millimeters, but 3 millimeters not bad, because they could be less than a quarter inch, they could be an eighth, and then you'll do a tip to tip on them, which we'll talk about. So honestly, I'm just going to keep it at 3 millimeters for now, accounting for a 1/8 fin with some tip to tip on top of it. And then number of fins. So there's no real perfect science to the amount of fins. It's very much so an engineering decision. There's pros and cons to having more and less. I normally fly 4 fins. We normally fly 4 fins, but 3 fins are very common. Six fins are pretty common as well, so kind of choose however you like. Of course, with the more fins at the bottom, you're going to have more drag, which means you're going to go slower. But with more fins down there, with more surface area, you can also be more stable. So it's kind of a play in between stability, speed, altitude, all of that kind of comes together. Fin cant we don't have to worry about because that's a tilt on the fins, which you do not want. And then right here is root chord, tip chord. So I'm actually convert this to a freeform because I like freeform a lot better. Here we'll have kind of the same options, but now when we go over to shape, we can play around with this here. So this is kind of, you can make these fins however you want. This is up to you for your design. We normally fly something called a clip swept delta. But yeah, honestly, choose fins that look cool to you. These are probably a bit small, but I'm going to keep them like this for now. That's perfectly fine. So the last thing for us to do is root fillets. Now, I think I actually have an example up here. So this is a model rocket booster section. And you can see these fins are attached, and then there's this piece of paper right here. So this paper is kind of acting as a fillet. So what a fillet does is the connection between the fins and the body tube, it smooths it out nicely. So it kind of distributes the force. Now this is super important to get a very nice fillet on your L1, which when we do a video on manufacturing an L1 level rocket, you will see. But yeah, this right here is what it's talking about when it says the root fillet. Now, just kind of from experience, I know my fillets, purely from how I do them, is normally around about 5 millimeters. They could be more. Fillet material, let's see what they got here. Steel, maple, JB Weld is what we most commonly use. So actually, you know what? I'm going to go with that just for now. All this does here is kind of account for the weight that will add. If you don't have this in your design, that's okay. Just know that most likely when you actually make your rocket, it's going to be a lot more heavy towards the end or by the fins. You're going to have to add some more ballast, but that's just how manufacturing goes. You'll notice your design and your actual end design or your end made manufactured rocket will differ a little bit. Most likely you'll end up with having to put some ballast in the nose cone. So I'm going to go with that for now. So our stability is quite low, so I am going to preemptively make these fins quite a bit bigger. So you'll see when I said stability, I was talking about this area over here. So to make our stability better, we can just make our fins bigger. So this is the stability. I'm going to remove this point here so it's a nice swept. So this stability here, it shows at Mach 0.1. Normally it shows at 0.3, but I've gone in my settings and I've changed this. So this stability gives you a good indication of how stable your rocket is, but there's going to be a more important place to look at for stability, which we'll get into at the end when we do our final design touches. But to stability at 0.1 Mach, I'll probably be maybe overstable, but this is fine for now. So an important thing about fin design is right here. This is what we call a swept here because we're swept back and we're also coming behind the back end of the airframe. Now, if I'll be honest, I would not recommend this for an L1 rocket. I would recommend something like this instead. If we get that nice, just quick and easy aligned up. Because the reason is the most common way for L1 failures is when you're recovering your rocket, it's going to be falling with the fins that are going to hit the ground first. If your fins are all the way back, there's a point of stress there that's going to hit on that tip and your fin can snap off. So this will hopefully be mitigated by a good tip to tip, but again, we're kind of designing these L1s to be nice and safe and work well. So I'm not going to sweep mine back. I'm going to put it perfectly aligned. I'm just keep it like that. Some nice basic triangular fins right there. And I'm pretty stable now, so I'm happy with that. Okay, so we have hit the very basics of this section. Now we need to go one further down, and that's about the motor retainer. So before we get started on that, let's head over to Canada Rocket Store. this is where, when you make your BOM or your bill of materials, this is where you should link to all of your stuff, except for like plywood and stuff that can be done at Elco. Anything that Elco supplies will do that first, but otherwise the more rocketry related things will be going through this Canada Rocket store. So if I go to build supplies, right here, motor retention and adapters. So right here are motor retainers. So I'm going to actually quickly go back to, where is it? Motor mounts. So here's examples of motor mounts, but that's not exactly what I want. So let's actually go straight to motor retention and adapt. Oh, there you go. I see motor tubes right now. Motor tubes. So this will be what your motors will be sitting inside. So that's that inner tube right here. The one we are looking for is this 29 millimeter. So honestly, this one I'm sure is just a bit thicker, but I'm going to go with this one right here. We'll most likely standardize this, and then you'll see why I had to look for a motor mount tube is our retainer. So go over to build supplies again, head over to our motor retention and adapters. So right now our motor just slips and slides inside of this motor mount tube, but it is free to go up and it's free to go down. So if it actually lit right now, it would just go straight through the nose cone, and if the recovery charge went off, it would go back flying outside of the motor mount tube. Not good. So we need a way of retaining this. So right here are the retainers I suggest. If we now scroll down to 29 millimeters, right here. So this is an Aerotech aluminum retainer. I want to find an Aeropack one because those are my favorite. Here we go, Aeropack. So a bunch of different options for the 29 millimeters. You'll see here this has an OD of 1.215, 1.2. So there you go. That's what I'm looking for. So this will be the retainer of my choice. Now you'll understand a lot better how these retainers work in the manufacturing video. For now, quick explanation is this right piece slips over your motor mount tube, you epoxy it in. So when you slide your motor in, it kind of sits flush with this little ring right here to put thrust through, and then this ring allows it to not fall back outwards. So this will be the retainer I'll be going for. I don't think they have a weight here, but from my experience, I recall, if I go to my body tube, and to add this, there's no real retention component. It's just going to be a mass component. So I'll add a mass component. I want it to be at the bottom of this component. And I want it to also be a little bit backwards. Length and diameter. So our diameter is going to be around about the diameter of our, so here's the OD of the motor mount tube. It's just going to be a little bit bigger than our motor mount tube. And length, again, you'll have to go back and refine this, but it's pretty thin. I'll do it like that. And then, yeah, I'll kind of put it half over. Just a general gist of where it's going to be. And then now mass. I recall mine weighing around about, I think, like 30 grams, but you'll have to weigh it when you actually get it because this is going to tank your CFG a little bit, but we'll go with 30 grams for now. So there is our little motor retainer. So I'm just going to call this my motor retainer. Boom. So now our motor won't actually go flying out backwards or forwards. So that's great. Now, the rocket here itself, it's actually kind of done if you don't want to have any recovery system on there, which you have to. This is kind of a missile that, well, we need rail buttons, but it would kind of work. So let's talk about rail buttons and then we'll go into recovery. So let's go back to the Canada Rocket Store, build supplies, and let's look here at launch lugs and rail guides. If I scroll down, here we go. This is what I'm looking for. So you will be flying on 10-10 rails. There's also 15-15 rails, which is what the Ringo family flies on, but you guys will be flying in 10-10. So you'll see how these work is here we have a rail button, and this nut will be attached on the back side of your airframe, and then that will screw straight in like that. So these rail buttons, let's go ahead and add them. So where are my rail buttons? Now, right here, we can see just some standard types of rail buttons. I'm just going to go standard 1010 because they're normally pretty accurate. I'm also going to do instant counts too, so it makes 2 of them. And then now, let's go bottom of the component, 0. Okay, so let's see which way. Okay, so now I'm going to put my upper rail button, which is this guy. Yep, I'm going to put it right on my CFG or real close. The reason for this is kind of that's going to be where you're rotating around on the rail and you want the least moment arm, and it's best if it's around about your CFG. It doesn't have to be perfect. The rule is technically it has to be either 1 caliper above or like it has to be within 1 caliper above or 1 caliper below. Again, below being a bit better, but it doesn't have to be perfect. So I'm going to put that guy there. Instant separation. Now I'm going to move this guy down a good bit. So remembering that the way that these are attached, if I head over to here, is with this nut on this back end. So we can't put this rail button right here by this centering ring. We could if we wanted to drill into it, but I wouldn't recommend that. So my recommendation would be either put it, well, of course, above or below. If you do decide to put it above, you're going to come into a problem when you do, well, something when you come into manufacturing is these rail buttons will be put in first, and then you have to slide the motor mount tube and centering ring on, but the centering ring won't be able to slide past this rail button, so you have to make a little notch in the centering ring, which is totally fine. That's pretty usual. Or you could put the rail button below. That works as well, and you can install it afterwards. Just because that's normally how I design it, I'm going to go ahead and put it pretty low down, but just above the centering ring. But it could be on both sides, as long as you have space for that nut. So, boom, there is our rail buttons. And I noticed that guy's a little bit below my CFG. That's fine. I can go in and fix that in a little bit if I have to. It doesn't have to be perfect. Okay, so now we could put this on a rail and launch it, but we need parachutes. So let's look at some parachutes. So let's go back to build supplies and parachutes and streamers. So I would recommend going with nylon chutes, plastic ones, or plastic streamers. You have to have a really small and light rocket to use streamers, and you guys don't really need the chutes with the spill hole, but if it interests you, you can. I'm going to go with nylon chutes though. So here we can see the diameter, 9, 12-inch, 15-inch. Let's see, how much do I weigh? Okay, mass with motors, I'm around about 1 kilogram. So just from experience, I'm probably going to want maybe let's start with a 24-inch, might be a bit too big, but inside of my body tube where the actual parachute will be stored, let's put a parachute. And then I said 24 inches. And then this will just be a generic Mylar 24-inch parachute. That's the one I want. Okay. And then you'll see it is right down there. I am going to move it a little bit this way. That's too far. Yeah, sure, that's fine. Packed length, I'll move up, but diameter, normally this packs pretty closely to the diameter of your actual rocket. So I'll just pack it like this. And then my packed length, I'll make this, I don't know, let's say 100. Yeah, that's around about right. Now let's see, is this parachute too big? If we go over to flight simulations, ground hit velocity of 7.96 meters per second. That's a little bit on the high end. Normally you want anywhere from 6 to 8, but tending towards the lower velocity. Honestly, I'm fine with that. It's definitely a little bit fast, so you definitely don't want fins going behind your rocket here because they're going to hit the ground pretty hard. I'm going to keep it like that, but you guys might want it to be a little bit more bigger so it hits the ground a bit slower. Okay, there's our parachute. Now let's head back on over. So let's head over to build supplies, shock cords. Now we actually have to connect our parachute, right? So right here, this is most likely what you guys could be using. You could also use some of this more bright shock cord, but this is what I normally use. Very strong. It is also Kevlar, so it's heat resistant, which is good for recovery. So this is what I'm going to go for. Now we can go in here and say shock cord. I'm going to put it, where is it right now? I'm going to put it smack dab in the middle. And then, yeah, sure, I'll keep it as this little node, but let's talk about shock cord length. So the general rule of thumb is your shock cord has to, of course, be attached somewhere in your lower airframe to hold on to it. Most of the time, that connection happens right here. It will connect straight onto the centering ring. So you could drill a hole in the centering ring, and then you can put the string through, and you can epoxy it in. Nice, simple connection. So the rule is from this point all the way to the top of the rocket, it has to be able to fully do that. And the length of my rocket's around about 1 meter. So from here to here is probably like 700 millimeters. It has to be able to do that and then double the length of the rocket. So shock cord from this centering ring to my parachute has to be around about 1,000 times 1,040 times 2, so we'll just go like 2,000-ish plus another 700. You know what? Let's make it a nice even number. Let's go 3 meters. So that's going to be the length of the shock cord from here to the parachute. Now, that's only, and then also we can change to Kevlar 12 strand, and that's a way too high mass. So I will override that mass to something more like, I think it'll be reasonable to say this could weigh up to 15 grams, but you're going to have to kind of go and look at mass for the Kevlar and how much that shock cord length will actually weigh. So yeah, grams per meter, and then you can go ahead and actually calculate it. Okay, so now we have a connection from here to our parachute, but we still have to connect to the nose cone, right? So in the nose cone, the easiest way to do it is if we head now over to our shoulder, if we do end capped. So what this will do is it will, well, put a cap on the bottom of our nose cone. So if I grab this guy right here, you can see here that if I pull this out, this nose cone has a cap, and then we can tie the shock cord, which is this right here, to the actual cap. So we'll have shock cord coming from the centering ring to the parachute, and then we'll have another line continuing from there connecting to our actual nose cone. So the length for that other line, as long as it's around about the length of your airframe, maybe a bit less, maybe a bit more, that's fine. So in my nose cone, well, actually, I guess I should put it in my airframe because it's going to be connected right there. It's going to be between the parachute and that cap. So let's get shock cord. And yeah, put it right there. Shock cord length, I'm going to go around with the length of my airframe. There's no perfect exact science here. And then I'll switch to Kevlar. Definitely not 50 grams. I'll go for like 10. Okay, perfect. So now we have a connection from our centering ring to our parachute, from our parachute to our nose cone, which will be capped right here to a connection. This cap could be made of PLA. You could put the shock cord through epoxy. You could put an eye bolt there if it's going to be a piece of wood. Honestly, sky's the limit on the connection there. So now we have this system kind of all done. So let's go back, build supplies. Let me see, what have I not covered? Miscellaneous hardware, something like swivels. I'd recommend maybe putting a swivel on your parachute just to make sure it doesn't wrap up and stuff like that. So to do that, we'll add a really small mass component, like super small, 5 by like 5. And then we'll put it somewhere close to the parachute. Yeah, right there. We'll call this guy the swivel. 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 Mass, I just know these are around about 2 grams normally, so I'll put 2 grams there. So now we have a connection from here to our swivel, to our parachute, from our parachute to our nose cone. So when the recovery charge goes off, which is what I talked about earlier right here, here is the recovery time. So after your motor burns, it then starts burning a delay charge, which will either burn for 14, 11, 9, 7, whatever seconds you choose. And then when that delay charge is done, it ignites a black powder charge, which will then pressurize this whole area, and then it will eject the nose cone. And then what that will do is that will pull the parachute out, right? Because we have this connection right here between the nose cone and the parachute. Now, this parachute is made out of nylon, but nylon and a lot of heat don't really mix. So normally what you need is, let's see, do they have parachute and streamers? Well, normally what you need is a little Kevlar blanket. So we have plenty of those that you guys can just put in, but those are super light, so I don't even think I'm going to account for that weight, but you probably should account for that weight on the Kevlar blanket, because that will wrap around your parachute, making sure that it does not melt in the really high temperatures that will happen when you have the black powder go off. So let me see, what do I have to still cover? Okay, okay, so now we have a good start of where our rocket is. Now let's actually see if it works. So let's head over to our flight simulations. So I'm going to bring that over here. Okay, so these are the simulation software, the settings I use. They're not like perfect, but they're not too bad. So average wind speed 3 meters per second, standard deviation of 0.5, intensity 10%, wind direction 90, and then now length of your launch rod. I'm going to change this to feet. You can guarantee it's at least going to be 8 feet. So let's just stick with that on 8 feet. That's all we really have to do here for the simulation settings. So I'll just say, okay, run the simulation. Okay, green means it's ran. Now let's see our results. So you can notice that after some changes, our ground hit velocity is 8.11. That's too fast. So let's go back to our parachute. And then now instead of 24-inch, let's go over here, parachutes. What's the next size up? So above 24-inch is 30-inch. So let's do a 30-inch generic Mylar. Boom, flight sims, run, ground hit velocity 6.49. Perfect, I'm very happy with that. Okay, let's plot this guy. So right here, I already have some things. This is going to be different than what you normally see. Very important that this launch rod clearance is clicked. This is the most important thing. By default, it isn't. Very important to have this clicked. And then now there's two things that we're going to be caring about here. Our total velocity and our stability margin calipers. So how stable we are. Then I'll go plot. I'll move this plot back over to the right screen. And then now to zoom in on Openrocket, you kind of just click and zoom on the places you want. So right here in the blue is our total velocity. So you can see we're increasing when we hit motor burnout, even a little bit before we start decelerating. And then we'll worry about recovery device deployment and all that in a sec. So I'm going to zoom in even more right here at the STARR. So launch rod clearance right here. Here's the important point. Look at our stability margin caliper. We're 1.5 off the rail. I'm very happy with that. Anything above 1.5 is very good. You don't really want to go below that. Technically, the rule is as long as it's above 1, it's safe, but I'd really recommend above at least a 1.5. So this is close to the minimum, but it's good enough for me. I'm going to zoom back out, and our highest stability is 2.9. Perfect. Overstable rockets are ones that are over 6 stability margin calipers. However, anything above 4.5, you're basically already kind of overstable. So I'd recommend to try your best to stay below that. But if you go slightly above, that's better than being not stable enough at the start. So for the first time in a while, my first design year actually worked out pretty well. I am pretty happy with this. But one thing I noticed is my recovery device deployment my apogee are really far off from each other. So my delay charge is going off way too early. So let's close here. Openrocket is nice and it gives us an optimum delay of 11.5 seconds. It calculates how long the delay we should be before we deploy. It even gives me a warning. My recovery deployment's a very high speed because I deploy my parachute before I even slow down all the way. So if we go to motors and configuration, if we go to select motor, here we go. My ejection charge delay is 5 seconds. So Openrocket said around about 11 or best. I'm going to change that to 11 seconds. Head back over. Head back over to Flight Sims. Run a sim. Okay. And then now you can see our velocity of deployment is drastically decreased, which is good because we don't want to snap our shock cord. And then now let's go plot. And then now you can see our recovery device deployment and our apogee are very close. It's never going to be perfect, but it's pretty darn near perfect in this case. So this I'm pretty happy with, honestly. Our stability is on the lower end, but it's not too bad. If we want, we could add ballast up there. And speaking of ballast, let me quickly show you how to do that. So ballast normally is in the nose cone, a little mass component that is at the top. We can just make it a little bit thinner and then move it inside of the nose cone. Yeah, sure, right around there. And then now if we're noticing that we are understable, we can add mass here. And if you pay attention to the stability over here, notice it went up, going up. But luckily for us, maybe, you know what, maybe we'll put 10 grams up there because then we'll leave even a little bit more stable off the rail. Okay. And this can be done with when you're, if you don't print it with the cap on, you can just throw some steel in there. Or if you do it right, you could print the nose cone and have this thing be completely filled with PLA. You'll just have to use like SolidWorks or Onshape to actually get the, make sure that it matches the amount of mass you actually want up here. But yeah, multiple ways to put ballast up there. But it's very common to need ballast, but try your best to design around not needing it because then you don't need to worry about putting it in. So let's say I was understable. We could have added ballast, we could have added more fins or made our fins bigger, or we could have chosen a motor with higher average thrust. Those are all possible solutions. Or we could have moved our mass up as much as we can to move our CFG up as much as we can away from our CFP. But let's say we're overstable, which doesn't happen very often. We can make our fins smaller. We could make our ballast less. Yeah, so there's multiple ways to combat that. My rail button's still a bit below my CFG, but I'm fine with that. So here, let me see, I think that is pretty basic on how to design an L1 level rocket. Now down here, I'm going to 3,500 feet and I'm going 0.6 Mach, pretty fast. Anything above around about 4,000 feet, you're going to need an altimeter for. Even above 3,000 feet is pushing it a bit. This is an L1 rocket. I would highly suggest making it bigger, making it beefier, making it stronger, and not going as high. So if you're flying above like 3,500, which I'm basically there, have a chat with us and we'll see if we can incorporate an altimeter in your rocket. And then, sorry, a GPS in your rocket, because you're going to need to track your rocket when it comes down, because you're going to be going pretty high up and you probably won't have eye connection the whole time. But if I was a little bit afraid of this, I could maybe add another layer of fiberglass or make it a bit longer. There's a bunch of different ways to go around not going as high, or make my fin smaller, make more ballast so it's heavier. There's many ways to do that. So yeah, I think that's my there. Let's head over here to quickly go over build supplies. So yeah, don't have to worry. Bulkheads will be cut out in Elco. Couplers, those will potentially also be made by you if you need couplers, but you shouldn't, because if you do a 1-bay deployment like this, or a 0-bay really, this is your coupler right here. It's printed with your nose cone. Don't have to worry about any of these fins. You don't have to worry about that. Launch lugs, rail guides. We talked about you needing miscellaneous hardware. So in here is like swivels and eye bolts and quick links. These are all things for your recovery system. And then motor clips, don't have to worry about. Retention inside there. Nose cones, you can decide to use a kind of a pre-made nose cone, but have some fun, design your own, print your own. Payload, don't have to worry about that. Parachutes and shock cords, so those are pretty important here. And then tail cones and transitions you can add if you want, but that will require a bit of extra work because we have tail cones in Ringo family, which we call boat tails, but normally L1 levels don't have that because it adds some complexity. So this is kind of how you design an L1. Now, where do we go from here? So go ahead, make your design. You can always talk with me over Slack and ask any kind of questions or over the L1 channel. Everyone, if you have a question, almost everyone has that one as well, so feel free to ask. And then once your design has been approved by me or Ethan, then you have to make a bill of materials, and this bill of materials will have links to everything on the Canadian Rocket Store that you need, or Elko, the material store, because we will be buying things in bulk, such as the motor mount tubes, because those can all just be standard. And yeah, everything else, like center rings, you will be cutting out. But yeah, once your bill of materials is done and you have a full approval on that, we will order you your parts. And then your next step is to watch the video on manufacturing, because now comes the fun and hard part of actually putting this thing together and then flying it. So yeah, I hope you guys kind of enjoyed this video. I know it's a lot, but pay attention to those timestamps if you have to kind of move around at certain places. Hopefully this answers most questions, but like I say, as always, if you have any, please do not hesitate to ask. So yeah, thank you guys. Have a wonderful, wonderful day.